This is part 2 of digital imaging. Digital image formation. The first step in digital image formation is scanning. The image is divided into a display to an array of pixels. Number 2 is sampling, and that's where we measure the brightness level of each of the pixels. And number 3 is quantization, where we have each piece of analog data is computed and assigned a discrete analog value, which is a number. So image processing begins with exposure field recognition. And this is where we're looking at the region of interest with the collimated edges. And those boundaries are detected so that the system only samples and manipulates clinically useful information. Secondly, we have the histogram analysis, where we're going to have histogram of the information. The ROI is created and automatic rescaling occurs. And then we have the image grayscale rendition, which is where we're looking at the lookup table being applied. So the histogram is a graph of the number of pixels in the entire image having the same gray levels. It's generated during initial processing. It allows the digital system to find the useful signal by locating the minimum and maximum signal within the anatomic regions of interest in the image. To generate a histogram, the scanned area is divided into pixels and the signal intensity for each pixel is determined. So this picture just shows the idea that we've got the actual image where we have some dark areas here, which is raw data, raw beam, I should say. And we have a collimated area. And so here's the collimated area that shows up on the histogram. And here's the raw data that shows up on the histogram. And in the center is the area that we're looking at that's actually we're using, the gray part. And so our actual characteristic curve is going to be a straight line as shown before, and it's going to, that's going to be the response of the image receptor. How to create a histogram is by looking at the number of pixels and the exposure. So the exposure is on the x-axis and the y-axis are the number of pixels. And we're looking at the, like for example, the values of number 1, which would be white. And so we have 3 colors that are white, and therefore there are 3 pixels that have a value of 1. And then if we go over here to number 4, we would have a different number, of course. We have 1, 2, 3, 4, 5 pixels that are that color. And so we go up and we find that there are 5 pixels that have a value of 4 of exposure. So anyway, after that's completed, that it's going to be graphed together and it creates a histogram. The histogram shape will correspond to specific anatomy and to the technique that was used. The system will perform a histogram analysis to determine the VOI and the EI. The VOI is the values or volume of interest used to locate the minimum and maximum exposure values for the body part. So it's what is important for that particular part. This area over here wasn't important because it's raw beam. The exposure indicator is the numerical value used to indicate the amount of exposure to the imaging plate or to the detector. It can be used to maintain acceptable image quality, and it can determine technical change necessary to provide optimal receptor exposure. Its accuracy depends upon reader calibration and appropriate exposure field recognition, and it's essential to QA and QC. So here we go. Here's the exposure indicator that we're showing here, the EI number. Here's the signal minimum and the signal maximum. Notice that we're excluding the collimated border because it's not part of our actual image, and we're excluding the raw image data raw beam because it's not necessary either. So the histogram is compared to a reference histogram, which there's one for just the cervical spine, for example, just one for an abdomen, just one for a knee, and it's going to compare them to it and fix it. A histogram, specifically a wide one, demonstrates high subject contrast. And the reason why is because it's going to include the white areas and all the way to the black areas. So it's going to include all the shades of gray plus the black and the white. If you have black and white, that's high contrast. Narrow histogram demonstrates low subject contrast. The example here is a mammogram where we mostly have just gray, and because the tissue is fatty for the most part. And so the idea is that while we have this at the center of the histogram, we don't have the white, we don't have the black within the signal range, and so that's why it's a narrow histogram and low subject contrast. If the histogram values are concentrated in the lower comparative values, the image appears dark or dim, and that's because this is photography with a positive image. It's flipped from radiography. So we would have the opposite side. And then the opposite occurs if histogram values are concentrated in the higher comparative values, which is over here, the image appears brighter light. And so that's looking at, again, the positive image. Histogram analysis error. This is where the exposure indicator might be misdetermined and a rescaling error is likely to occur. The appearance is a light or dark image with an incorrect EI number, and the exposure field or collimated margins are not correctly located, the histogram analysis will not be performed on all exposure data. There are many causes for histogram analysis errors. A very common one is poor collimation with scatter, over-collimation, so collimating too much. Prosthetic devices, large tissue density differences, barium in the fundus on a chest x-ray, more than one image on an imaging plate. Back to collimation, it's not having the correct borders, so you have to have at least two borders. So it's just there's all these histogram analysis errors that can occur with CR. And so it makes it, it's not going to come out perfectly like you would with DR. So here's an example of a case that was an OR where the image was taken where there's two recognized borders, and then a second image was taken and they didn't get that second border. And so therefore they're used exact same technique, but unfortunately they have a very light image, and it's not because of anything different than it's the same patient, not anything different otherwise. So just one underexposed border did this one. A matrix is a series of boxes. It consists of rows and columns, M and N. The dimension of the image is M and N, which would be M times N. And the FOV is the field of view, determined by the size of the detector. Matrix size is determined by the size of the pixels. So on the left-hand side, we have 3 rows and 3 columns. So we have a total of 9 pixels, but they're really big pixels compared to the ones over here in the blue. In the blue, we have 9 columns and 9 rows, the same size outline as the pink. It's just that the pixels are now smaller. So smaller pixels are going to be the opposite of the matrix size. So over here, we have a 9 by 9 matrix where we have small pixels, and we have a 3 by 3 matrix on the left-hand side because we have 3 rows and 3 columns. And the 3 by 3 means that we have 9 pixels, where in the 9 by 9 matrix, we have 81 pixels. A pixel is 2D data. It's also known as a picture element. It contains a number, which is a discrete value, as shown here in the diagram, and it reflects tissue characteristics being imaged, which are brightness levels, and represents a shade of gray. It can be seen down here at C. The pixel size is equal to field of view divided by matrix size. One thing extra is that pixel density is the number of pixels per unit area. So which image has higher spatial resolution? So hopefully you picked the one on the right, image B. Image A was taken with a system that was back in the 1970s, was an 81 by 81 matrix, so very small matrix size. And the one on the right is a 1024 by 1024 matrix size. So the larger the matrix size, the higher the spatial resolution. A voxel is known as a 3D data. It's a volume element. So tissue voxel information is converted into numerical values and expressed in the pixels, and these numbers are assigned brightness levels. Bit depth determines the number of shades of gray. It is the number of bits per pixel. Bit depth ranges from 8 to 32 bits. Each pixel will have 2 to the k power of gray levels. We'll take a look at this on the next slide. K-bits implies that every pixel in the digital image matrix M times N is represented by K binary digits. A higher bit depth offers more gray shades. It's also known as density resolution. So if we have a bit depth of 1, we're going to take 2 to the first power. All of these are always 2 starting off with 2's. So 2 to the first power, and 2 to the first power is 2. So it has gray shades of 0 and 1. We always have to start off with zeros with computers because computers have zeros and ones. So bit depth of 6 would have 2 to the 6th power, which would be 64 shades of gray. So it's going to go from 0 to 63 as far as the gray scale. A bit depth of 8 is going to be 2 to the 8th power, which is 256 shades of gray. So it's going to have 0 to 255, and so on. So it just continues on like this. To the bit depth of 10 would be 2 to the 10th power, so that's 1024. So we'd have a grayscale of 0 to 1023. And it also shows you which imaging systems we use for these. And what's very amazing is ultrasound. It has a bit depth of 32. So that's a very large number of gray shades. So what's the effective bit depth of the number of gray shades? Well, it increases. So if you increase the number of increase the bit depth, we go from 2 to the 2nd power, which is down here, and we go to the 2 to the 8th power, which is 256 shades of gray. We're going to have more gray. So the number of gray shades is going to increase. Dynamic range is the range of the exposures that may be captured by a detector. It's the number of gray shades that an imaging system can produce, and it's identified by the bit depth of each pixel. So raw image data is what we start off with the characteristic curve. And pre-processing gives us corrections for a processing image, and post-processing makes improvements for presentation. So let's begin with pre-processing with corrections. So automatic rescaling is our first pre-processing for corrections. And we have 3 images that were taken here at different mass values, and the EI number kept going up, but the overall image is the same. The brightness level is the same. Flat fielding is where we equalize the response of each pixel to a uniform X-ray beam. The purpose is to correct the non-uniformity of intensity in images. So image A has different intensity throughout the images or brightness throughout the image, and so image B is after flat fielding was applied automatically by the computer, and it corrected it, so it's uniform now. So it's uniform brightness if you think about it. Dead pixel correction is going to assign digital values to each dead pixel row or column. An example of dead pixels would be one that would happen on a phone. Another example would be a column of dead pixels. So in those cases, there would be dead pixel correction that could take care of that. The lookup table. So we go from a low contrast image, we go to the lookup table, which is in the computer, to a high contrast image. So it's going to control contrast. Edge enhancement is high pass filtering. It's going to sharpen an input image that appears blurred. So the advantage is at the halo artifact. And on the left-hand side, we have the blurred image. On the right, we have the edge enhancement that was applied. And this is typically used in mammography and angiography. Equalization improves contrast. And what it does is it spreads out the histogram. In the top image, we have the histogram where we have just mostly on the left-hand side. And then the histogram on the bottom part is where it's been spread out. And when we spread out the histogram, we're going to increase contrast, which gets back to the idea of a wide histogram has a higher contrast. Smoothing is low pass filtering. This intentionally blurs the image, thus reducing noise and the displayed brightness level of the pixels. The advantage is the details compromise and appears blurred. The smoothing was applied in the image on the left-hand side. Post-processing are improvements. So we have annotation where we label the image, window leveling, and window width, which is expanding the grayscale to visible. Modification, improving visualization and spatial resolution. Image flip, which is reorienting the image presentation. Image inversion is making white black and black white. Subtraction is improving image contrast. Pixel shift, which is re-registering an image to correct for patient motion. And region of interest, determining the average pixel value for use in quantitative imaging. So windowing is our second one. We have the window width, which is on the left-hand side, and the wide window width is going to have a low contrast image. Narrow window width is going to have a high contrast image. And then we have brightness, dark images versus light images. So window leveling is going to control brightness, and window width is going to control contrast, and that's with post-processing. Mattification, as we just saw talked about just a moment ago, is going to allow visualization of a smaller part. Image flip. Image inversion allows you to go from taking structures from white to black and black to white. Digital subtraction and geography. This is where we have the first image where we have just the anatomy. In the center image, we have the contrast with the anatomy. And the third one is where we've subtracted. And the purpose is to increase contrast. And of course, we have image inversion that took place as well. Pixel shift is to re-register an image to correct for patient motion. So the idea is that on the image on the left-hand side, the patient had moved, and the image on the right is where it was corrected. Instead of having to repeat the study, all we have to do is use software. ROI identifies the region of interest and computes the mean pixel value. So showing the original image versus the image region of interest and the equalized region of interest image. Pan, scroll, and zoom are just looking for careful visualization of precise regions of an image. Cropping and masking, applying a black border to eliminate the white areas around a properly collimated border image. It reduces eye strain that can be caused by the increased brightness levels. And then finally, stitching. Stitching is where we stitch together, for example, a scoliosis study or long bone study. And this concludes our video lesson for part 2 of digital imaging.